Welcome to this scientific lecture on inversion, a powerful method where we deliberately reverse our assumptions to create innovative solutions. Inversion means doing the opposite of conventional approaches. Instead of following standard assumptions, we flip them completely to discover counterintuitive solutions. Let's begin by understanding what inversion means in engineering and problem solving. Inversion is the deliberate act of reversing conventional assumptions about how a system should work. Instead of asking how to achieve a goal directly, we ask how to achieve its opposite. For example, instead of heating something to make it warm, what if we could cool something to generate heat elsewhere? This is the essence of refrigeration. Think of inversion like reading a problem statement in a mirror. Everything appears reversed, but the fundamental relationships remain valid. Inversion has a solid mathematical foundation. Let's explore how reversing parameters changes system behavior. Consider a simple differential equation that describes heat flow or diffusion with boundary conditions. This equation describes temperature distribution T along position X, with heat generation Q and fixed temperatures at boundaries 0 and L. The standard approach assumes temperature at position 0 is high and temperature at position L is low, causing heat to flow from left to right. But what if we invert this? We reverse the boundary conditions completely. Now T at 0 equals the low temperature, and T at L equals the high temperature. Heat flows in the opposite direction. This graph shows the temperature profiles. The red line represents the standard case with decreasing temperature. The blue line shows the inverted case with increasing temperature. Inversion is especially powerful in control systems, where we can flip feedback signs. In standard negative feedback control, we subtract the output from the desired value to create a stabilizing error signal. The control signal U equals the proportional gain Kp times the error E, where error equals reference R minus output Y. Now here's the key question. What happens if we invert the feedback sign and use positive feedback instead? With positive feedback, the error becomes reference plus output. This typically causes instability and oscillation. The result is that the system becomes unstable in the classical sense, but these oscillations can actually be useful in certain applications. This graph compares negative feedback in green, which decays to stability, versus positive feedback in red, which grows and oscillates. Let's examine a concrete numerical example showing how inversion affects energy efficiency. In a standard heating system, we consume energy E to directly raise the temperature of a space. Energy for heating equals mass times specific heat times temperature change. For 50 kilograms heated by 20 Kelvin, with specific heat 1000 joules per kilogram Kelvin. This gives us 1 million joules or 1 megajoule of energy consumed. The inverted approach uses a heat pump that moves heat from a cold reservoir to a hot reservoir rather than generating heat directly. The coefficient of performance equals heat delivered divided by work input, which equals hot temperature divided by temperature difference. This can be around 4. The work required equals energy needed divided by COP, which is 1 megajoule divided by 4, giving only 0.25 megajoules. This represents 75% energy savings simply by inverting our heating strategy from direct heating to moving heat. Refrigeration cycles are a perfect example of inversion in action. They seem counterintuitive but are highly effective. Conventional thinking says that coldness naturally flows toward hot areas, or equivalently, heat flows from hot to cold. Inverted thinking asks, what if we force heat to flow from cold to hot, opposite to its natural direction? A refrigerator uses a compressor to pump heat from the cold interior to the hot exterior, inverting the natural heat flow direction. The vapor compression cycle uses mechanical work to reverse the natural flow of heat energy. Energy balance. Heat extracted from cold side plus work input equals heat rejected to hot side. For typical values, we might extract 3 kilowatts from the cold side, input 1 kilowatt of work, and reject 4 kilowatts to the hot side. Another fascinating inversion example is vibratory conveyors, which oscillate materials instead of moving them steadily. Standard conveyors use steady motion and rely on friction to grip and move material continuously. But what if we invert the motion from steady to oscillating? This seems counterintuitive for moving things. Vibratory conveyors use rapid oscillations that move material forward through a clever combination of inertia and friction. The platform oscillates back and forth rapidly. During forward motion, the material slides forward. During backward motion, inertia keeps it moving forward. The platform position x equals amplitude a times sine of omega t. Velocity equals a omega cosine omega t. The net result is forward motion because the material advances more during the forward stroke than it slides back during the return. Advantages include gentle handling of fragile materials, no wear on belts since there are none, and significantly lower maintenance. Typical specifications include frequency of 20 to 60 Hz, amplitude of 1 to 5 millimeters, and effective speed of 0.1 to 0.3 meters per second. Another powerful inversion is to immobilize the part and move the environment instead. In standard machining like a lathe, the part rotates while the cutting tool remains relatively stationary. In inverted machining, we fix the part and rotate the tool or cutting head around it. The part remains fixed in the center while the tool orbits around it in a circular path, performing the cutting operation. Why invert this arrangement? Because heavy or large parts are difficult to spin accurately at high speeds. Examples include large turbine rotors, telescope mirrors, and ship propellers that may weigh several tons. Response time comparison shows the standard approach takes about 2.5 seconds to reach operating speed, while the inverted approach takes only 0.8 seconds. This gives roughly a 3 times acceleration advantage when working with heavy parts. One of the most counterintuitive inversions is stochastic resonance, where adding noise actually improves signal detection. Standard signal processing wisdom says to suppress noise as much as possible to improve the signal-to-noise ratio. But what if we invert this principle completely and add noise deliberately to the system? In stochastic resonance, an optimal amount of noise actually enhances the detection of weak signals that would otherwise be invisible. Here we see a weak signal in blue that's barely detectable. Adding optimal noise in red creates fluctuations that help threshold detectors capture the signal. The output signal-to-noise ratio equals input SNR times a function of noise standard deviation. This function peaks at an optimal noise level. Applications include sensors detecting subthreshold mechanical vibrations in structural health monitoring. A real example is cochlear implants that use controlled noise injection to enhance speech perception in deaf patients. Signal-to-noise ratio improvements of up to 6 decibels have been measured with optimal noise levels. Let's develop a general mathematical model that captures the essence of inversion across different domains. Consider a general system model characterized by a parameter p that controls some aspect of behavior. The system dynamics are given by dy dt equals some function f of state y, parameter p, and time t. In the standard case, parameter p is positive and the system behaves in the expected manner. In the inverted case, we make p negative, which flips the fundamental behavior of the system. We have p standard greater than 0, and p inverted equals negative p standard, which is less than 0. As a concrete example, consider a spring mass system where p represents the spring stiffness. The equation is m times acceleration equals negative k times displacement, where k positive gives stable oscillation. But if we invert the sign to plus kx, the system becomes unstable and exhibits exponential growth instead of oscillation. The normal spring in green oscillates stably. The inverted spring in red grows exponentially, representing completely opposite behavior. When we invert systems, how does this affect measurement errors and uncertainties? In standard measurement systems, error decreases as we average more samples according to the square root of n law. The standard deviation of the average equals the individual standard deviation divided by square root of n samples. In inverted sensing strategies like dithering, we deliberately add controlled error to reduce systematic bias. Consider a numerical example with a sensor that has 0.1% systematic bias and 0.5% random noise. Without dithering in 100 samples, total error is 0.1% bias plus 0.05% random error, giving 0.15% total. With dithering, we reduce bias to 0.02%, but increase random noise to 0.7%. Total error becomes 0.09%, which is lower. This represents a 40% error reduction by counterintuitively adding noise to break up the bias. Thermoacoustic devices use thermal inversion to convert sound into refrigeration or power. Conventional thermodynamics says when we compress a gas, it heats up, and when we expand it, it cools down. Thermoacoustic inversion uses sound waves to create temperature differences without any moving mechanical parts. Acoustic waves cause gas parcels to oscillate. As they compress and expand in the presence of a stack, heat pumping occurs. Heat flux equals 1/2 times pressure amplitude times velocity amplitude times area times sine of phase angle phi. The key parameter is the phase angle between pressure and velocity oscillations, which determines the direction of heat flow. Coefficient of performance achieved ranges from 1.5 to 2.0 for cooling, which is competitive with standard vapor compression systems. The huge advantage is no moving mechanical parts, leading to very long lifetime and environmentally friendly operation with no refrigerants. Inverting boundary conditions in partial differential equations reveals deep mathematical insights. Consider the wave equation describing a vibrating string with both ends fixed in place. The wave equation is second partial of u with respect to t equals c squared times second partial with respect to x. Standard Dirichlet boundary conditions fix displacement to 0 at both ends, at positions 0 and L. What if we invert to free ends instead of fixed ends? This changes to Neumann boundary conditions. Neumann conditions specify that the derivative of u with respect to x equals 0 at both boundaries. The consequence is completely different mode shapes and resonant frequencies for the system. For fixed ends, frequencies are nc over 2L for n equals 1, 2, 3. For free ends, n can include 0, giving a static mode. The mode shapes differ fundamentally. Fixed ends show sine functions that go to 0 at boundaries. Free ends show cosine functions with 0 slope at boundaries. Cryogenic cooling systems use extreme inversion of conventional heating approaches. The goal is to cool an object to near absolute zero, around 4 Kelvin, for applications like superconducting magnets. We cannot use standard vapor compression refrigeration at such extremely low temperatures due to thermodynamic limitations. The inverted strategy uses Joule-Thomson expansion of helium gas, which actually cools when expanded at low temperatures. The Joule-Thomson coefficient mu equals the partial derivative of temperature with respect to pressure at constant enthalpy. For helium below its inversion temperature of 40 Kelvin, mu is negative, and cooling occurs during expansion. Temperature change equals mu Jt times pressure change, with coefficient negative 0.06 Kelvin per bar and 100 bar pressure drop, we get 6 Kelvin cooling. A multi-stage process with several expansion stages reaches 4 Kelvin, enabling superconductivity in materials. Sometimes, inverting the time scale of a response can yield surprising benefits. The standard assumption is that faster response time is always better for control systems. But the inverted question is, when might deliberately slower response actually be beneficial? The answer is that thermal mass and averaging can suppress high-frequency noise disturbances. Consider a fast system with time constant 0.1 seconds versus a deliberately slow system with time constant 5 seconds. The fast system responds quickly to set point changes, but also amplifies every noise spike. The slow system acts as a low-pass filter, providing a stable average output that rejects high-frequency disturbances. Application includes temperature control and precision instruments, where stability matters more than speed. Noise reduction of 20 decibels has been achieved simply by deliberately slowing the thermal response. Let's summarize the key inversion strategies we've covered in this lecture. Inversion strategies include boundary condition inversion, control system inversion, thermal inversion, and response time inversion, each offering unique benefits and insights in various fields.